speaker is Marcel Gort, a master's student with the supervision of Professor Jason Anderson.
PhD student.
So, pardon me, PhD student. Giving a talk on parallel routing for FPGAs.
Thanks, Ron. Right, so the work is titled Deterministic Multicore Parallel Routing for FPGAs. And it's work that we'll be presenting at FPT in December in Beijing. Okay, so the motivation for this work is that compiling a design to an FPGA is taking longer and longer. So it currently takes too long. The problem's getting worse for two main reasons. One is that FPGAs themselves are getting bigger. There's more silicon, and therefore you can put a larger circuit on them, and the CAD problem is just getting more complicated. The other factor is that uniprocessor performance isn't really improving all that much anymore. The silicon's all going to multiple cores on a single die. So the key to keeping CAD runtimes reasonable is either to use those multiple processors, so in other words to parallelize the CAD algorithms, or else to come up with more scalable new CAD algorithm. So we've chosen to go the parallel route for this particular work. So this is an outline of the talk. I'll start by going over the FPGA CAD flow from a high level, and then talk about maze routing, which is kind of the core subroutine of FPGA routing. Then talk about Pathfinder, so the different parallelizations techniques that I have worked on the maze routing level and on the Pathfinder level. So that's why I talk about both those algorithms. And then talk about the two parallelization techniques that I implemented, one fine-grained, one coarse-grained, and their associated results. This is the high-level CAD flow for FPGAs. We start with a circuit. It can be HDL or BLIF or something like that. And the output is a bit stream that can be downloaded to an FPGA. So the first three steps take that circuit, that's the input, and then convert it to an FPGA, a net list of FPGA logic blocks. So these can be labs or clusters or CLBs or whatever you want to call them, with some connections between them. Placement assigns XY locations, so physical locations, to each one of these logic blocks. Now this was actually parallelized, or a work was published in 2008 by Altera that parallelized this step. So what we were actually working on is parallelizing routing. So placement and routing are kind of the two biggest steps in terms of how much time they take, so we're focusing on routing. And routing aims to make the connections between the physical logic blocks using the existing FPGA architecture, all while avoiding shorts. Okay, so this is a graph kind of view and data structure view of maze routing. So the problem of routing a net is handled by maze routing. So if you think about routing a net, say from a source to one or more sinks, you can represent that problem using the graph, where the vertices are routing resources, so either wires or they can be CLB pins or IOs, and then the edges are the programmable switch that can connect those different routing resources or vertices. So the problem of finding, say, a path from a source to a sink on an FPGA can be translated into a graph problem of finding the shortest path from two vertices, or a lowest cost path. So on the right is a priority queue. Now what the priority queue is for is to organize the nodes that we'd like to explore into by their cost. So the lowest cost node, which is the best one to explore, will be at the top of the priority queue. And here the priority queue is structured as a binary heap. So the top is the kind of the head of the queue. Okay, so we start by exploring the source of a net A. So we want to get from source A over here to sink A over here. So we first explore the source, and we push the neighbors onto the priority queue, because these are the nodes that we want to explore next. Now we've determined that the cost of node 3 is lower than cost 2, so we're going to pop that. It was at the top of the priority queue. The cost kind of takes up two components. There's two components to the cost. One is the distance that we've traveled so far from the source to that node, and the other element is an estimation of the distance, or it could be delay, from getting from that node to the sink. So now we add the neighbors of 3 to the priority queue, so we've got 8 and 7, and then we pop again the lowest cost node, which is 8, and keep doing that until we get to the sink, and then we do a trace back to the source to get a rep. So we've now found the shortest path. Now if we're going to do the same process to get from source B to sink B, I'll just skip all the intermediate steps, but this would be the shortest path for that net. Now you see there's one node in the middle that's now shared between the two signals, and that's not allowed because that's a short. So we have a conflict here, or we can say that there's congestion at this particular routing resource node. So to get around that, Pathfinders kind of overlaid over this basic maze routing. And Pathfinder's job is really to try and resolve these conflicts or this congestion. And it's actually quite good at doing this. It forms the basis of commercial routers by Xilinx and Altera, as well as routing in VPR. And it uses maze routing as a subroutine. Okay, so this is a high-level view of Pathfinder. Pathfinder starts by doing basically what our example maze routing did, which was to find a route for all of the nets. It tries to find basically the lowest cost, ignoring all congestion. And then once we have an idea of kind of the nodes that are the most congested, we can assign more expensive costs to those congested nodes, essentially making them more expensive to use. And what will tend to happen is that when we go to reroute signals, they will tend to avoid those congested nets because a lowest cost path will tend to avoid these high cost nodes. So we'll tend to have less congestion after we reroute the signals, and if there's still shorts that remain after we reroute all the signals, we can increase the congestion further, or increase the cost for congested nodes further, and keep doing this basically until the algorithm converges and we have a short free routing. So this route all signals is really the core of the Pathfinder algorithm, and this is the part that we parallelized in the coarse-grained approach. So I said that route all signals seems like you do it in parallel, or kind of the signals are independent, but they're really not. The algorithm starts by ripping up and rerouting the very first signal, and then updating the congestion information based on the route, then ripping up and rerouting the next signal, etc., until all the signals have been ripped up and rerouted. And the thing to take away from this is that the route of this particular signal is dependent on the previous route, because the previous route will have affected congestion, and so will affect the costs of the nodes. So you can't just kind of trivially split this up between a bunch of processors and expect that the algorithm converges. It won't. So we need to communicate some congestion information. Okay, so we parallelize Pathfinder in 2 ways. The first way is a fine-grained approach where we actually parallelize the maze routing of a single net. The second approach is a coarse-grained where we parallelize Pathfinder. And this may be kind of what you think about if you were to think about how to try and parallelize routing, which would be to just split up the nets between different processors and route the nets in parallel. So we do that and we communicate some congestion information. And what's interesting is that kind of we wanted to explore these 2 methods to parallelize routing, but additionally we found that these 2 methods are orthogonal, so we can actually use them in tandem, where some cores are, you can have, say, the net split into 2 sets, where 2 processors are each working on 1 set. So you actually have a split on a coarse-grained and on a fine-grained level. So we can explore that space as well. Another key aspect of our work is that it is deterministic. So there's been previous work done on parallel routing that's either worked on a planar architecture, which isn't kind of realistic modern FPGA architectures, or it's been non-deterministic. It says here deterministic, but that should say non-deterministic. And determinism basically means that from run to run, the routing result will be exactly the same. So if you have a specific, with the caveat that you're running with the same configuration of number of cores. So this is critical for debugging and testing of the CAD flow, and particularly from a vendor's point of view, if a customer has a problem, you have to be able to reproduce that. So this is a must. Okay, so the fine-grained approach, we'll talk about that first. With the fine-grained approach, we use p-threads. The part that we actually parallelize is the costing of nodes, so determining the cost of using a node before we add it to the priority queue, and adding that node to the priority queue. So those two steps, when you put them together, represent, for some benchmarks that we ran on VPR routing, about 67% of total routing runtime. So it's a good spot to focus with modifying just a small amount of code. Now the other thing, if you try to think about this, if we're trying to parallelize adding to the priority queue, there could be multiple processors trying to access the priority queue at the same time. So what we did is we split the priority queue. If we have n processors, split it up into n priority queues. So you have the lowest cost node can be at the head of one of the n priority queues. So if you're trying to get the lowest cost node, you have to check the head of each one. And we do the synchronization using barriers that are very low overhead because they use busy wait signals rather than mutexes. Okay, so in our previous example, we had maze routing. So if we were to pop the nodes, the neighbors of the source onto the priority queue, processor A would add node A to priority queue A, and processor B would add node 3 to priority queue B. So this can be done in parallel costing and adding. Okay, so this is kind of a flow of how the algorithm works for the fine-grained approach. On the left is the steps undertaken by the main thread, and on the right is this, you can have one or more of these helper threads that undertake just the costing and adding to the priority queue. So the main thread also costs and adds to the priority queue. And then we have two barriers that control the flow of the algorithm. The first barrier, so if we go to the first step, the first barrier actually stops the helper thread from costing and adding nodes to the priority queue before they're available. So that we start with the main thread getting the lowest cost node and from the priority queue, and then expanding around that to find out the neighbors. And then it splits the neighbors between the helper threads and itself. And then it's ready to cost the nodes. So it arrives at the barrier. And a barrier is a construct where all the members participating in the barrier have to get to it before any of them can leave. So it's just kind of like a meeting spot where everyone has to get there before people can leave. So once they're both at these barriers, we can cost the nodes in parallel, add them to the priority queue in parallel, and then we get to the second barrier. And the role of this barrier is really to avoid the main thread trying to get the lowest cost node before the priority queues are up to date. So let me go back there, and the helper thread will go back to the third barrier. Okay, so we ran some experiments to try and figure out what the runtime would be like using this method. We used some benchmarks from the MCNC benchmark suite and also from the heterogeneous benchmarks that are included in VPR. And we only use them if the runtime plus parse time is greater than 10 seconds, because we want to focus on the larger benchmarks. We use an FPGA architecture with length 2 unidirectional wires, cluster size of 10, LUT size of 4, and we use the channel width that's the minimum channel width plus 30% for all our experiments. And we only measure route time, so we don't actually measure parse time. And we perform the results on two different CPU architectures. The first is an Intel Core 2 Quad, and the second is Core i5, and they're both 4-core architectures. The main difference you'll notice is that the Core 2 Quad has shared L2 caches between CPU 0 and CPU 1 and CPU 2 and CPU 3, but doesn't have a unified level of cache for all the processors, all the cores. And the Core i5 doesn't have any shared L2 caches, but has a shared L3 cache across all processors. So what this means is if you want to do, say, synchronizing a barrier, which means basically what it comes down to is a global variable. In the Core 2 Quad, you can store that global variable in L2 cache and have both processors access it. But in the Core i5, you have to go all the way to L3. So it's a bit slower for that reason than the Core i5. But if you want to synchronize between, say, CPU 0 and CPU 2, it's much slower for the Core 2 Quad because the common level of the memory hierarchy is the main memory. Whereas in the Core i5, it's the same as the L3. So this makes our results make a bit of sense. On the y-axis is the speed up relative to single core, And on the x-axis is the number of cores that we ran, and we have the 2 bars for the 2 different architectures. So this is kind of a negative result in that we see that it doesn't really scale past 2 cores. We get an okay result with Core 2 quad with 2 cores, really because all of our synchronization can happen in the L2 cache. But then as soon as we move to 3 or 4 cores, synchronization has to happen through main memory. And because it's fine-grained, this is happening millions of times during the run, so it actually slows down. The Core i5 sees a bit of speed up, but not as much as the Core 2 quad for the 2 cores because the synchronization is going through L3. So this is a negative result, but it's interesting because the runtime is very dependent on the CPU architecture. So with different CPU architectures, say if there was a high-level unified cache or there were direct links, you might see some better performance. And for all these results, there's no deterioration in the quality of the results in terms of the critical path delay and the wire length, and it's, again, deterministic. Okay, so the coarse-grained approach, we get some better results for this. So if you remember, this is the flow for the Pathfinder algorithm, and what we want to parallelize is the route all signals step. So say we split that up into 2 steps with the 2 different processors. The same boxes, except we added a box here which was send and receive congestion. So after we rip up and reroute signals in parallel, update the congestion in parallel, now we have some updated information that we can send to the other processor. And the other processor can choose to whether or not it wants to receive it. We are using MPI, which means that the different processors are actually running different instances of VPR, so there's no shared memory. All the communication is explicit using MPI messages. Right, so the nice thing about using MPI and having a distributed memory model is, and running different VPR instances, is that we didn't have to worry about locks for all of the data structures. So it was actually fairly quick to get this working. We just had to worry about that the communication was correct and implementing what we wanted to. There's a few different types of messages that you can provide in MPI. There's blocking send and receive messages, which mean that if you issue a blocking or send message, you can't continue with execution until the corresponding receive or send has been issued. Non-blocking send means that you send the data to a buffer and immediately you can continue with execution and that information can be ready for pickup whatever. A non-blocking receive means that you can ask for a message, and if that message hasn't been sent, you just continue with execution like nothing happened. So there's 2 main challenges with just a coarse parallel approach. The first is to maintain determinism. So the way we maintain determinism is ensure that the updates that we get from the other processors, the congestion updates, happen at the exact same point in the algorithm for every iteration. And the way we do that is we use blocking receives. So whenever we say that we want to receive an update, if that update hasn't been sent yet because of some, the time that it was sent is slightly different from when to run, we'll stall. So we're trading off stall time for determinism. So the key then to getting a good speed up is to try and reduce that stall time. And the way we can do that is, first of all, the send messages can be non-blocking, that doesn't affect determinism. And the next is that we want to avoid receiving updates if we don't think that the updates have been sent yet. So we're going to do that by trying to estimate when the messages are going to be sent by the other processor and only trying to receive the updates after we think that they've been sent. Okay, so the basic idea of our approach is first we want to estimate how long each net will take to route. I'll talk about how we do that estimation in a couple slides. But the basic idea is if we have some estimation metric. So here we have 5 nets that we want to route. Each one has an estimation of how long it will take to route. And then we want to split those nets up between the different processors. And we want to do that so that the amount of work that each processor does is approximately equal for good load balancing. So processor A has net 0, 2, and 3, and processor B has net 1 and 2. And if you sum up the work estimates for each one of those sets, you get approximately equal work for each one. So once we have the split, we can route the nets in parallel, and we want to try to minimize stall time so that we only want to receive updates if the corresponding update has already been sent. So this is to keep our congestion up to date. Okay, so we have here the work estimates that we are replicated from the different processors because it is distributed memory, so they each have a copy of the work estimate. We have 2 processors running, and each one has a set of nets that it's been assigned to route. We have some NPI buffers to send and receive messages between the 2 processors, and we have some work counters. Now what the work counters do is, if you're looking at this from processor A's point of view, work counter A would just estimate, would count how much work has been done so far in the iteration to route the different signals. Work counter B, on the other hand, is kind of a checkpoint at which we should anticipate that processor B will have sent an update. So for example, the first thing we do is to initialize the work counter. So again, from the perspective of processor A, we've done no work so far, so work counter A is 0. And we should expect to receive an update when we've done 6.1 units of work, because at that point, the first net in processor B will likely have completed. So it will have sent an update and we should be able to receive it. Okay, so we start routing the next signal in parallel, and actually processor A finishes first because it doesn't have to do as much work for its net. We update the work counter A to indicate that we've done now 3.2 units of work. We send an update to pickup whenever processor B wants to receive it, and the update contains the updated route for net 0. So then processor B, when it receives that, will update the congestion to reflect that new route. And then we check whether we should receive an update. And the way we check that is to check whether our local work counter is greater than the checkpoint, or work counter B. In our case, we've done less work than we need to have done to anticipate that processor B will have sent an update, so we don't request an update. We route next signal, update the work counter, so we've now done a total of 5.6 units of work, send another update, again check whether we should be receiving an update, and the answer is again no, because the sum of the work done for our 2 first nets is not as much as the work done for processor B's first net.
Question?
Yeah.
So processor B is doing its work before it knows what the result of processor A's first route is that right?
Yeah. So these work estimates are estimates that we've taken from the previous iteration.
My question is more relating towards determinism. I think I heard you say it's deterministic if you use the same number of processors. Is that right?
So yeah, if you have, it'll run the same if you run it on 4 processors arranged in a coarse-grained configuration, or it'll run the same if you have 2 processors arranged in coarse-grained. You
mean the 4 and the 2 will run the same?
No, we'll not run the same. 2 will run the same as 2, 4 will run the same as 4.
Okay, so you've messed around with the definition of deterministic to be for the same processor configuration.
So I think the alternative, which is when it runs the same, is like when everything runs the same, there's another
Serial equivalent.
Yeah, serial equivalent.
So this is not serial equivalent.
Not serial equivalent, but it is deterministic. I think that's consistent with the definition of
I see.
deterministic.
And it's because of this, because processor B doesn't know the result of processors B work on net 1 goes forward without knowing the result of what A did on net 0, right?
Sorry, what's because of this?
So the reason it's not serially equivalent is those 2 things are going on along in parallel, and whatever A did could affect what B could do.
The reason it's not serially equivalent is because the split of the processors will be different from, the split of the nets between the different processors will be different for 2 cores or say for 4 cores. So you'll update.
Right, and then yeah, I understood that, and
Okay.
it's because B doesn't wait for A to finish its work before it gets going. And that could change, if it knew what A had done for the first net, it might change what it did on the second net.
So if you started, say, with the max number of cores, say being 8, and you updated or you synchronized after every single net, And then when you run 4 cores, you synchronize it for every, say, 2 nets or something, then you could get some sort of serial equivalent. You could get the updates happening at kind of exactly the same time. But that's not.
Sorry, you're trying to say how you would make it serial equivalent?
Yeah, so,
Oh.
right, but this is, it's not serial. Okay, so we don't request an update at this point because we haven't done enough work to justify it. So then we go again to route the next signal from processor A's point of view. Now in the meantime, processor B will finish routing its signal, and it will update its work counter to say now it's done 6.1 units of work. And you'll notice that the work counter A, which is processor B's checkpoint at which it should receive an update, is still stuck at 3.2 because we haven't received the first update. So we'll send our update, which is the net1, the updated route, and then we'll check whether we should receive an update. And because we've done more work than that first update from processor A did, then we will receive an update. We'll first update the work counter A to say that the next time we should receive an update is when we've done 5.6 units of work. Receive an update, and we'll check again whether we should, before we route our next signal, we should check whether we should receive another update. And the answer is again yes, because we've done enough work to justify it. So R1 net here takes more work than the 2 first nets of processor A. We'll update our work counter, so now the next time we should receive an update is 9.1. And we can continue in this way until all signals are routed. I should mention that at the end of the iteration, we received all the outstanding congestion updates. Yeah.
Question.
Yeah.
When you dispatch the net to the workers, do you consider the geographic location of the net?
Not yet.
If there are 2 nets won't overlap with each other, you don't have to send the update.
Yeah, that's a really good point, and that's probably the best way we can improve this. So we don't do that for the work for this paper. Yeah, that's a good suggestion. So in the previous example, the quality of kind of our estimation really relied on the quality of our work estimates. So if we get really good, ideally close to perfect work estimates, we can reduce the stall time in the blocking receive calls. Additionally, we can do a better job doing load balancing right off the bat, so that we just have from a high level, more equal distribution of work between the different processors. So we used 4 estimation metrics. We tested them out. The first is the number of sinks for a signal. The second is the bounding box, so basically the length of the wires, length of wires would be correlated with bounding box. And the third is the number of nodes explored in the graph in the previous iteration, and that should be strongly correlated with the time that it takes to route a net. The fourth isn't one that we actually used, or that we're not suggesting that you actually use this. This is just kind of for comparison. The fourth is the time taken, so the actual microseconds taken in the previous iteration. But this causes non-determinism because that can change from run to run, and so yeah.
Sorry, just a quick question. Number 3, the number of nodes explored in previous iteration. That's basically to gauge how much data you have cached, right? Is that the motivation for it?
The motivation is that the time that it takes to route a signal is really tied up with how many nodes you cost and add to the priority queue. And so a really good way to estimate the amount of time that's deterministic from run to run is how many nodes we add to the priority queue. Right, so this time we'll just use for comparison. It's kind of like the ideal case of how good we could get. So the first example here is what we consider the really kind of hard example, or the first set of results. So on the y-axis we have percentage stall time as a proportion of total runtime, and on the x-axis we have the number of cores running. So you can see that the number of nodes explored is quite a bit better than the other 2 deterministic metrics that are work estimation metrics that we have. But for this case, it's still not quite as good as time. So 25% versus 12% stall time or something like that. And you can also see that the stall time grows with the number of cores. And the reason for that is that the actual work that's being done by each processor is decreasing as we're increasing the number of cores, but the communication is not decreasing. So as a proportion of total runtime, it takes up a greater proportion. Okay, this next example is a different benchmark, CLMA, and this is the best benchmark in terms of stall time, in terms of how close we could get to the ideal case, which is using time as an estimation metric. So in this case, the number of nodes explored is pretty much the same as time, in some cases even better. So definitely we want to use num nodes explored, and all the other benchmarks are somewhere in between, so we get pretty close to an ideal amount of stall time given given the ideal case. Okay, so these are the overall results for the coarse-grained approach using 2, 3, and 4 cores. On the y-axis is the geomean speed up relative to the single core case. On the x-axis are the 2, 3, and 4 cores with coarse-grained configuration. You can see that with the Core 2 quad, we get about 2.1x speed up. The speed up isn't quite as good for Core i5, but it's in the same ballpark. Now these next 3 bars are kind of the more unusual cases that we ran experiments with. So this middle bar is course 8 star, and what that represents is 2 Core 2 quads running over a network. So with MPI, you can split the computation between different computers running over a network. So a lot of the communication is actually going through the network. So that's why we don't get quite the same speed up compared to 2 to 4. If you compare 2 and 4 and 4 and 8, we don't get quite the same speed up. Also the communication, there's more communication. The last 2 bars are combined coarse and fine-grained approach. So 2.2 is 2 coarse, 2 fine, 4.2 is 4 coarse, 4 fine. So each one of the coarse processes is split into 2 threads. And what you see here is the results, so you can compare 4.2 and this 8 and 2.2 and this 4. So the results are not as good as just strictly using coarse. But what's interesting is if you look at the speed up between 4 cores and 8 cores here, just using coarse, and 4 cores and 8 cores here, this seems like it's probably more scalable. So we get kind of 2 different curves going in terms of the scalability of the 2 approaches, so that you may actually get, for some architectures or a certain number of cores, benefit from using a mix. Okay, these are the results for the Core 2 quad for 2, 3, and 4 cores for all of the different benchmarks. The best result we get is about 2.45x for a couple of the benchmarks here, and then the worst, for 4 cores, and then the worst is over here, we would get about 1.5x for 4 cores. The rest are somewhere in the middle. Okay, so I'll conclude now just saying that this is the first deterministic parallel routing approach for modern FPGAs, so non-planar FPGAs. It runs on commodity hardware. You get around 2.1x for 4 cores. And you actually can choose whether you want to use a coarse-grained approach or a mix of coarse and fine, or just fine. And that could be architecture dependent. In our future work, we'd like to do what Hannah suggested, which is to split the... So the main problem, we know where our bottleneck is, and that's in the stall time. So we need a way to reduce the stall time. There's 2 ways to do that. One is to have better work estimation metrics, but we saw that our work estimation metrics are actually pretty close to the ideal, unless we want to somehow predict how that changes from iteration to iteration. So the other way to do that is just to reduce the amount of communication, and that provides less of an opportunity to stall. So one way to do that is to split the nets up geographically, so that makes some updates redundant. So that's what we're looking to do for a general version of this. The other things we'd like to do is to look if we have more cores or different types of architectures, how does the trade-off between coarse and fine work out, and whether it makes sense to actually choose the distribution of the parallelism between coarse and fine grained based on the actual CPU architecture running. Okay, so that's it. You can find the paper on my website. Any questions?
Right, so my understanding of the mechanism of estimating the time to route a net is to deliberately ignore ignoring the results, congestion results from an earlier net in order to reduce the stall time, so you don't serialize the whole thing.
Sorry, can you repeat the question?
My understanding of you trying to estimate the route time of a net
Yes.
is so that you can choose to ignore the congestion results from an earlier net. So you don't serialize the routing of every single net.
So it's,
Like on the, for example, on processor B, your first net didn't get the congestion data until the third net
of processor A,
processor A.
right.
So that
So
should
the
have some QOR impact, right?
You might think that it would, it doesn't. For so the amount of information that we're losing here is not enough to affect the QR. So I didn't actually mention this, the quality of the results is not at all impacted for the coarse-grained result either.
So it should be very slightly impacted.
It's better in some cases, worse in some cases. It's within 0.5%,
Okay.
so it's not enough for me to make it. But you're right, it should be slightly impacted. It could be that it's just that maybe it takes an extra iteration of the routing. That could be but I didn't see an impact on that.
And that is also the source of not serially equivalent.
Yes, that's right.
Okay. And a suggestion is, what if instead of using so you have a estimated work time on the other processor in order to judge whether you should do a receive.
Yeah.
What if you add an offset to that to absorb communication latency? Could you arbitrarily reduce stall time
Right.
to 0
So
by
that's
adding more latency?
that's an interesting avenue of research as well. I think that's a good idea. The question is whether you have if you have any overall load balancing issues, then all that stall time will get pushed to the end. But you should be, if it kind of all averages out, you should be able to experiment with adding offsets. Maybe we can push it a bit further without affecting the quality of the
Right,
results.
so adding an offset would absorb communication latency, it would absorb variation in your estimate, it won't absorb overall load balance.
Yeah, that's a good suggestion as well. Yeah,
Right, question from the chat room is, have you thought about implementing the parallel features of the routing on an actual FPGA?
no, that's too much work. Yeah. Yeah, Chandler?
So did you compare this to non-deterministic parallel routing?
Yeah, so the non-deterministic approach is like 3.5x on 4 cores. So it's quite a bit better. But, so from speaking with some people associated with the vendors, it seems like if it's non-deterministic, it doesn't matter what the speed up is, it's not worth it.
Because there's a lot of work recently that tries to get determinism from what's otherwise non-deterministic programs, right? And most of them, they require some special hardware, but there are some approaches that can run on commodity hardware. So maybe you can use that tool and run them with non-deterministic parallel then, and that would give you deterministic routing.
Right,
And compare
could
it
be.
with your thing.
Could be. Yeah, that's interesting. I hadn't thought of, because yeah, I'm not sure how exactly that approach works, but yeah, that's something that could be looked at. Yeah.
So for the FPGA you're routing for, you're using min routing plus 30%. Have
That's
you
right.
tried with different metrics? Because that min width plus 30% usually guarantees, well, you should be able to find a good path. So
Yeah.
I was wondering whether or not you tried it with fewer routing channels and see if that actually impacts I guess your QOR.
Not thoroughly. So I've done little spot checks and it seems to work out, but I haven't done a thorough set of experimental benchmarks. Do you think that if that had any impact, it might be on the fine grain because the number of nodes you had would be different and that sort of thing. So, but that's a good idea to do that just for thoroughness' sake. Yeah.
So in the coarse-grained parallelization approach, would it be possible for a CPU core while installing, could it speculatively do useful work, and then once it actually gets the update, decide to keep the work it's speculatively done or redo it? Could you do something about that, or is the nature of the problem such that you can't reliably predict whether the work you're speculatively doing will be ruined by the actual update?
So I'm trying to think of what work it could do, and it couldn't start to route the next. It couldn't do anything that has to do with congestion. So any sort of costs, anything that has to do with the cost of the nodes, it couldn't do because those costs might change with the update.
Could it guess?
Wouldn't that also kind of solve your solving your geographic problem and saying that the congestion numbers won't change if the routes are very far apart.
Mhm.
Just go ahead and start working, and if an update comes in saying that it's been changed, then you just delete your work.
If the condition is changed and it affects, and it ruins your guess, then you have to do it again.
Yeah.
But if it's okay, it's compatible with the way you guess, then you can keep, it's kind of like transactional memory in that way.
Mhm.
Well, and you could
Yeah,
track it in a coarse-grained way, right? You don't have to say each node was disturbed. You could say this region got disturbed or didn't get disturbed, and therefore didn't disturb the speculative route.
Yeah, so that's interesting. I hadn't thought of that. I mean, if there's any change, yeah, if there's any change in the route, then you would just scrap it and do it again. If there's no change in the route, then maybe you could keep it.
And if you knew the other computer didn't even visit the same area
Yeah.
that you were visiting, kind of like Anna's suggestion,
Right.
then you can just
You
accept
can do
it,
it.
yes, right?
Yeah, that's interesting.
How big was it's a priority queue, like that's the number of nodes that are contested, right? So any of those nodes in the queue are, viewed or updated, just and then you're gonna have a problem. But like, is this hundreds of nodes, thousands per day? How complicated is it?
Hundreds, I think.
So far,
It
that's
depends completely on the size of the FPGA and the size, but even then, the priority queue is cleared out after each neck. So if I'm trying to think if the actual final route was identical and you pop different nodes to get there, whether you could ignore that difference as long as the final route was the same, it's possible. That's interesting.
How the memory scalability, because for each work you need to duplicate the entire routing resource graph.
Yeah, so the currently it's the amount of memory for the routing times the number of processors. So it scales linearly. If we did some sort of geographic partitioning, it's possible that you could try and split up the routing resource graph and then maybe not get a memory overhead. And maybe the nets that cross those boundaries, you have, say, points on the intersection or on the boundary that stay the same or something like that. Something could be done, but the current iteration does not scale well for memory. Yeah.
Just a question about your benchmarks and the virtual chip that you tested on. All of your benchmarks are single clock designs, or?
Yes.
And the chip is just a simple tile, no block grams or anything like that?
There's, there are some, one block RAM that's split. So it's the architecture that Jason Blue worked on with, there's the 36 by 36, that's, I think you can split it into 18 by something. Is that right?
It's a multiplier.
It's a multiplier, sorry, not a block RAM.
Right.
Not a block RAM. Yeah.
You're using UCAR 5.0, right?
Yeah.
So that one,
The K4-N10.
yeah, that one, there's no splitting in that, that's monolithic block.
Okay, one monolithic multiplier. So I popped that into the like realistic architecture. So so it's a multiplier but no memory.
Great, any other questions? Well, let's thank our speaker, thanks.